Warm greetings and good afternoon, my dear friends and students. Today I am going to take a video lecture on the maximum shear stress and maximum bending stress, which will be occurred on a cantilever beam, which is having an UDL of 10 kilonewton per meter and for a span of 2 meter and a point load of 10 kilonewton is acting at the free end of a cantilever beam. So here, first of all, you have to find the reaction. The reaction at the fixed support, that is fixed end, I call it as A, and the free end is B, and the midpoint as C, that is 1 meter from the free end or from the fixed end. So the maximum reaction, vertical reaction occurs at the fixed end A. The value is 10 plus 10 into 2, 20. So 10 plus 20 kilonewton, that is equal to 30 kilonewton, which occurs at the left support at this fixed end A. Now, what about the shear force at the free end B? The shear force at the free end, if you are taking the right hand side of the free end, point load, right side point load is plus 10 kilonewton, and at the fixed end, that is at A, the shear force is maximum, again that is equal to plus 10 plus 10 into 2, that is 20. So 10 plus 20 is equal to 30 kilonewton. So the shear force diagram, if you are finding it from A fixed end A to free end B, what will happen here? It is plus 10 above the horizontal line you have to draw, and having a trapezium, the maximum value at the fixed end, which is of 30 kilonewton. So the maximum shear force occurs at the fixed end, that is equal to 30 kilonewton. Now, the cross section of the beam is 250 mm wide and 500 mm depth, which is of a rectangular cross section. You know, the moment of inertia about the neutral axis for a rectangular section is B into D cube by 12. So that is equal to 250 into 500 cube by 12 in terms of mm per 4. If you simplify, you will get the value of phi in terms of millimeter to the power 4. So the maximum shear stress is equal to, for rectangular beam, is equal to 3 by 2 into Q average. So 3 by 2 into Q average is something but maximum shear force, which is of 30 into 10 power 3 Newton divided by area is 250 into 500. So 3 by 2 into 30 into 10 power 3 divided by 250 into 500, close the bracket. So we'll get the value which is of say 0.38 Newton per square millimeter. So this maximum shear stress will occur at the neutral axis of the cross section of the beam. For example, this beam, which is a rectangular section, top and bottom fiber, neutral axis at the center. So here 0, 0, the maximum shear stress which is of parabolic, which is of a parabolic one, so which is of at the neutral axis 0.38 Newton per square millimeter. So this is about the shear stress distribution diagram across the cross section of the beam. Now, so the maximum bending moment will always occur at the fixed end in the case of a cantilever beam. So that is equal to minus 10 into 2, then minus 10 into 2 square by 2. What will happen? So it is minus 20 minus 20, you will get minus 40 kilonewton meter, which occurs at the fixed end. For example, this is the fixed end and this is the free end. So at the fixed end, we are getting a maximum moment of 40 kilonewton meter. Okay, which is of hogging moment because of negative moment. So you have to plot, for example, this is the horizontal axis of the beam. Now we are plotting negative value because of hogging moment from one end to other end, free end to fixed end. What will happen? So it is of a parabolic curve of this type. So maximum bending moment of this parabolic curve, which is of minus 40 kilonewton meter. So in the case of maximum bending stress, we have to use the pure bending equation, the first two term. It is m by I is equal to sigma max by y max. Now I want sigma max, that is the maximum bending stress. So that is equal to the maximum bending moment m divided by the moment of inertia of the neutral axis into the maximum fiber distance y max. So here we are getting 40 kilonewton meter. So 40 into 10 plus 6 from kilonewton meter to Newton millimeter divided by I is b d cube by 12. That is 250 into 500 cube by 12 into y max is 500 by 2, so that is 250 mm. So if you are simplifying this calculation, we are getting 3.48 Newton per square millimeter. So the maximum bending stress in the case of cantilever beam, right? So above the neutral axis, you will get tensile stress. Below the neutral axis, all the fibers are subjected to the compressive stress in the case of the cantilever beam. So the maximum bending stress is 3.48 Newton per square millimeter. So if you are drawing, so this is a vertical line cross section of the beam. So above the neutral axis, you will get, right, the tensile stress I am putting in this way. Here also the triangle compressed stress at the bottom fiber, 250 mm, 250 mm. What will happen here? So tensile stress, which is of triangle and 0 at the neutral axis. Then in the case of below the fiber, 0 and maximum, right, which is at the point 0 to maximum, again a triangle. This is a reversal of the above the neutral axis and below the neutral axis. Now, so maximum bending stress will occur at, for example, this is a rectangular beam, top fiber and bottom fiber. That top fiber you are getting 3.48 Newton per square millimeter tensile stress, and it will be a triangle. After that, it will happen 0 at the neutral axis, then coming to maximum at the bottom fiber, which is of compressive stress, that is equal to, right, 3.48 Newton per square millimeter. So this is how we are finding the maximum shear stress and maximum bending stress value, and you can plot the shear stress distribution across the cross section and the maximum bending stress across the cross section of the beam. So like that, you can find the corresponding section either 1 meter from the right end, or 0.5 meter from the right end, or 1.5 meter from the fixed end. We can find the corresponding shear force and bending moment. For that, what will be the shear stress distribution and bending stress distribution, like that you can work out. And this is about the maximum shear stress bending stress for a cantilever beam subject to UDL and point load at the free end. And we have completed the shear stress distribution diagram and the bending stress distribution diagram across the cross section of the beam. Thank you very much for patient listening. God bless. வாழ்க வையகம், வாழ்க வளமுடன்.